Welcome to our deep dive into this fascinating world where wireless networks basically optimize themselves.
Yeah.
Become self-optimizing.
Yeah.
You sent us two really cool papers from a research group at UPenn,
Mm-hmm.
and they're both focused on resource allocation.
Yes.
The first is from 2019, and it kind of sets the stage with deep neural networks.
Mm-hmm.
And then the 2022 paper takes it up a notch using graph neural networks.
Right. And what I think is really interesting about these papers is how they frame resource allocation as a constrained optimization problem.
Okay.
As a researcher, you deal with constrained optimization all the time.
Yeah.
And it's like you're managing a limited budget, and you have to distribute that budget effectively across this network.
Okay.
So you have power, bandwidth, time slots, and you have to figure out how to distribute those effectively.
So it's all about how can we squeeze the most out of the network.
Yes.
Whether that's, maximizing data rates or minimizing latency. But at the same time, we have all these constraints that we have to juggle.
Yes, and you hit a really key point, which is that it's very, very challenging to actually find the best solution.
Okay.
Especially when you think about like a wireless environment, which is very dynamic.
Right.
And it's constantly changing.
Yeah, things are moving around all the time.
Exactly. And so, these optimization problems often involve very complicated mathematical functions.
Yeah, I'm already starting to see why AI could be really helpful here.
Yes.
But before we get to the AI part of it, I'm really curious, how do they formulate this resource allocation as a constrained optimization problem?
Yeah.
Like, how do those real-world constraints, how are they represented mathematically?
So the way that they start is they define this global network utility function.
Okay.
And this function basically captures the performance of the network. So for example, that could be the sum data rate achieved by all the users in the network. And then they introduce constraints that represent limitations of the system. So for example, each device might have a maximum power limit.
Okay.
Or you might want to guarantee a minimum data rate to each user in your system.
Right. So the goal is to maximize that network utility function.
Yes.
While staying within all of those constraints.
Exactly.
It sounds like a real balancing act.
It is a balancing act. And this is where things get even trickier because often these optimization problems are non-convex.
Yeah.
And what that means is that there are multiple local optima. And it can be very difficult to find the global best solution.
Okay.
Because if you use traditional optimization methods, they can get stuck in those local optimization, and they might not find the true best allocation.
So even defining this problem mathematically is a challenge in and of itself.
Yeah.
Now, they bring in this idea of Lagrangian multipliers.
Yes.
I vaguely remember this from my optimization courses, but can you give me a refresher? Why are those so useful here?
So Lagrangian multipliers are really a clever mathematical trick.
Okay.
And they allow you to transform a constrained problem into an unconstrained problem.
Right.
So imagine you're trying to maximize a function, but you can only be within a certain region.
Okay.
What a Lagrangian multiplier does is it creates this new function that penalizes you for being outside of that region.
So instead of having those hard boundaries like you can only be in this region, now it's like we have this penalty zone.
Exactly.
That kind of guides us towards the feasible solutions.
Right. And this leads to something called the dual problem.
Okay.
Which is like a shadow version of the original problem.
Okay.
But in this new unconstrained space, and often it's much easier to solve this dual problem.
Okay.
And then relate the solution of that dual problem back to the original problem.
So this dual domain concept sounds powerful, but is there any catch?
Yeah, that's a good question. You're right to be cautious because there can sometimes be a duality gap. And what that means is that the solution that you find in the dual domain might not perfectly match the true optimal solution of the original problem.
Okay.
But what's exciting is that these researchers have found ways to bridge this gap using deep neural networks.
And this is where that 2019 paper by Eisen and the team comes in.
Exactly.
So how do they use deep neural networks to actually tackle this resource allocation problem?
So they essentially train a deep neural network to learn the optimal resource allocation policy.
Okay.
So you can think about this deep neural network as a black box. It takes as input information about the network state, like the channel conditions and user demands and power limits. And then it outputs the optimal resource allocation for each device.
So instead of having, some rigid mathematical model that we're relying on, it's like we're just letting this deep neural network learn from experience,
Yeah.
and adapt its strategy over time.
Exactly. And they combine this DNN with this really clever Primal-dual learning method. And this allows them to train the DNN effectively, even though we have this duality gap.
Mm-hmm.
And it leads to a model-free approach for resource allocation.
Model-free, that sounds like a big deal.
It is a big deal.
So that means you don't need to know perfectly everything about how this system works.
Yes.
In order to start optimizing.
Exactly. You hit the nail on the head. And this is really, a big change from traditional methods,
Okay.
which require you to have a very deep understanding of the dynamics of the system.
Yeah.
This opens up all these possibilities,
Yeah.
especially in complex scenarios in the real world,
Okay.
where it's hard to model everything perfectly.
This is incredibly promising.
Yeah.
Before we get ahead of ourselves and talk about that 2022 paper, can you walk us through how these deep neural networks are actually learning?
Yeah.
I want to make sure we've got a good grasp on that.
So imagine you have all these different network scenarios.
Okay.
And each scenario has, a different set of channel conditions.
Mm-hmm.
User demands available resources.
Yeah.
And for each scenario, you also have this target, which is like the optimal resource allocation that you would like.
Okay, so it's like we're showing the deep neural network all these flashcards.
Yes.
With the network scenario on one side,
right.
and then like the best allocation on the other side.
Exactly. And just like with flashcards, the DNN learns by trying to match its output to the target allocation for each scenario.
Got it.
And the learning process involves, adjusting the DNN's internal parameters so that its output gets closer and closer to this desired target over time.
I'm curious, like, what information is the DNN actually using to make these decisions? It can't just be looking at the raw numbers, right?
That's right. You need to have some signal processing expertise.
Okay.
And so the input to the DNN is this carefully engineered representation of the network state. And this might include things like channel gain measurements, which tell you how strong the wireless links are between different devices.
Okay.
And also user data rate requirements and other constraints.
So it's like we're taking all this raw data from the network.
Yes.
And converting it into something that the DNN can actually understand.
Exactly. And feature engineering is really important here.
Okay.
Because the better you can represent this network state, the better the DNN is going to be able to learn and make good decisions.
Makes sense.
Yeah.
So how do they know how well the DNN is doing?
Yeah.
Like, how are they evaluating if it's finding these good resource allocations?
Right. So they use a metric called the network utility. And remember, this is the function that we talked about earlier that captures the overall performance of the network.
Right.
So like the total data rate or some measure of fairness.
Okay.
And so during training, they compare the network utility that's achieved by the DNN's allocation to the utility of the ideal allocation for that scenario.
So we're seeing, okay, how close did it get to the best possible performance?
Yes. Okay. And the goal of the training process is to minimize the difference between those two utilities.
Got it.
So in other words, the DNN should learn to produce allocations that are as close to optimal as possible.
That makes sense.
Yeah.
You mentioned earlier this Primal-dual learning method.
Yes.
And how that helps with that duality gap that we were talking about. Can you unpack that a little bit more for me?
Yeah. So remember, the duality gap arises because if we solve the dual problem, we don't always get the exact solution to the original primal problem.
Right.
So the Primal-dual learning method addresses this by incorporating both the primal variables and the dual variables into the training process. So it encourages the DNN to find solutions that not only minimize the dual problem, but also satisfy the constraints of the primal problem.
Got it. So it's this two-pronged approach.
Exactly.
We're optimizing and we're staying within the bounds of what's possible.
Yeah. And the results are quite impressive. In their paper, Eisen and the team show that this Primal-dual learning method, combined with this powerful DNN, can achieve near optimal performance in a bunch of different wireless network scenarios.
That's awesome. It feels like we're almost to this point where we have these intelligent networks that can just adapt and optimize themselves without us having to constantly intervene.
Yeah.
But let's move on to that 2022 paper by Wang and the team, which brings in graph neural networks. I've heard a lot of buzz about GNNs lately.
Yeah.
Especially in the context of wireless communication.
Yeah.
So what makes them so well suited for this problem?
So you're right. GNNs are very exciting.
Yeah.
And they're well suited because they deal with data that has this natural graph structure. And that's exactly what we have in wireless networks.
Okay.
So you can think of each device as a node in this graph, and the communication links between devices as edges in the graph.
So they can capture those relationships between devices.
Exactly. Okay.
And how they kind of influence each other.
And how resource allocation decisions in one might affect another.
Exactly. That's one of the really key advantages of using GNNs for this problem.
Okay.
Is they allow for this decentralized decision-making.
Centralized control. That's a huge step.
It is a huge
towards self-organizing networks.
Yeah.
So can you go a little bit deeper into how these GNNs are working in this context?
Yes.
I'm curious how each device is learning from its neighbors.
So imagine each device has its own little GNN, which is like a mini brain. And these GNNs can communicate with each other by sharing information about their local states, like their channel conditions and their current resource usage.
So it's like this network of little tiny AI agents that each have their own perspective, but then they're working together to optimize the whole system.
Exactly. And each GNN learns to refine its own allocation policy based on the information that it receives from its neighbors. And the beautiful thing about this approach is that you don't need a central controller to dictate everything.
Right.
Each device can adapt and make decisions autonomously.
So cool. But I imagine training these GNNs must be pretty tough.
It is challenging.
How do they make sure all these agents are learning to cooperate effectively and that we're getting this globally optimal solution?
That's a great question. And that's where the Wang paper introduces this really cool technique called unsupervised primal-dual learning for GNNs.
Unsupervised learning. So that means we don't need those example targets.
Exactly.
Those flashcards that we were talking about.
That's right. This is a big difference from traditional supervised learning. Because in this unsupervised approach, the GNNs learn purely from the interactions in the network. So there's no external guidance on what the optimal allocation should be.
That's wild. How do they learn what's good or bad then?
That's a good question. And that's where the primal-dual part comes in.
So remember the primal-dual framework that we talked about earlier with Lagrangian multipliers and the dual problem?
Right.
They apply a very similar concept here.
So
the GNNs are trained to minimize this global loss function that incorporates both primal and dual variables. And this guides them towards solutions that are both feasible and effective.
So it's like this reward system that's built into the network itself that encourages them to find those good allocations without explicitly telling them what to do.
Right. And the results are pretty amazing. The Wang paper shows that this unsupervised primal-dual learning allows the GNNs to converge to near-optimal resource allocations in a bunch of different network settings. And they even outperform some traditional centralized optimization approaches.
That's awesome. Can you walk me through some of the specific advantages of using this unsupervised approach?
Yes.
I'm really starting to see the power of this unsupervised approach. What are some of the specific advantages of using it for GNNs in resource allocation?
So first of all, it's incredibly practical because you no longer need to collect these labeled data sets with optimal allocations, which, as you can imagine, can be very time-consuming and expensive.
Especially for large networks.
Exactly. And so this makes it much easier to actually deploy these techniques in the real world.
Where we don't always have all that data. That's a huge win for practicality. What else?
So another key advantage is scalability. So unsupervised learning allows these GNNs to handle really massive networks with potentially thousands of devices. And this is something that would be very difficult to do with traditional centralized approaches. So this really opens up the possibility of managing these increasingly complex networks of the future.
So not just optimizing the resource allocation, but doing it at a scale we've never seen before.
Exactly. And there's even more so. The GNNs that are trained with this unsupervised method, they exhibit this property called permutation equivariance. And what this means is that they can adapt to different network topologies. So a GNN that's trained on one network can be very easily transferred to another network without having to retrain it from scratch.
That's incredible. So it's like this universal resource allocation expert that can just jump between different networks.
And we also have robustness.
Okay.
So these GNNs are inherently designed to deal with the asynchronous nature of real-world networks.
Okay.
So they can tolerate things like delays and variations in device clocks.
Yeah, because not everything's perfectly synced up in the real world.
Exactly. And so this makes them much more resilient to these imperfections that we see in practice.
All right, so we have all these advantages that sound really promising.
Yeah.
But let's zoom out a little bit here. What are the broader implications of these research findings?
Yeah, I think what we're seeing is really a paradigm shift in how we design and manage wireless networks. So these papers are pointing towards this future where networks are much more intelligent, they're much more autonomous, and they're able to provide this seamless and optimized user experience, even as the networks are becoming more and more complex. And the conditions are changing all the time.
It's like we're moving away from this manual control to like self-driving networks that can just figure it out on their own.
Right.
What about you as a researcher?
Yeah.
How can these techniques help you in your work?
Oh, the possibilities are endless.
Okay.
So, if you're working on optimizing 5G networks or 6G networks, these techniques could be really game-changing.
Okay.
Imagine using GNNs to optimize beamforming in these massive MIMO systems. Or to allocate resources dynamically in these really dense, heterogeneous networks.
Yeah, it sounds like we have this whole new toolbox of techniques to use.
Yeah.
I'm sure there are still challenges and open questions, though.
Of course.
Where do you see the most exciting opportunities for future research?
So one promising direction is to think about incorporating more sophisticated learning algorithms, like reinforcement learning, into this framework.
Okay, so instead of just reacting to what the network conditions are right now, they can actually start to anticipate what might happen.
Exactly.
And proactively change their strategy.
That's the exciting potential of reinforcement learning.
Very cool. What else?
Another area that I think is ripe for exploration is how to deal with the security implications of these decentralized approaches.
That makes sense.
Yeah.
Anytime we have an autonomous system, we need to make sure that it's trustworthy.
Absolutely.
And secure.
Yeah. And finally, I think there's a lot of potential to think about how these techniques can be applied beyond communication networks.
Okay.
So, imagine using them to manage swarms of drones or to optimize traffic flow in smart cities, or even to coordinate resource allocation in distributed computing systems.
Wow. The applications seem limitless.
Yeah, I think so.
Well, on that inspiring note, I think we've reached the end of our deep dive.
Okay.
We've covered a lot of ground today, from the basics of resource allocation to these really advanced GNNs and unsupervised learning techniques.
Yeah.
I hope this discussion has given you some new ideas to explore in your own research.
I hope so, too.
And, these papers that we talked about, they're just the tip of the iceberg. There's so much more out there to learn.
Yeah.
So keep learning, keep experimenting, and who knows, maybe your next breakthrough will be the one that revolutionizes wireless communication.
I agree. It's an exciting time to be working in this field.
Awesome. Well, thanks so much for joining me today.
It was my pleasure.